Good morning, everybody. Welcome to 5.4 Inference for Sampling. Let's get into it. We'll start with the first definition, simple random sample. So simple random sample, basically just like random sample, is a sample chosen in such a way that every group of n individuals, let's get this in here, every group of n individuals in the population has an equal chance to be selected as the sample. Ooh. Equal chance to be selected as the sample. Yeah, so we talked about this before. Um, this is the ideal situation for sampling a group. No bias here. Just basically you take everybody's name in a hat and you pull their names out or a random number generator, different types of ways of doing this. But that's a simple random sample. Second one, sampling variability. The fact that different random samples of the same size from the same population produce different estimates. And we saw this last week when we did the lyrics, the Beyonce song lyrics. Um, we had Google do the random number generator, and pretty much everybody in the class got different averages, right? But we graphed them and we saw the variability there. We saw how spread out it was. But yeah, everybody's going to have somewhat of different samples, right? The samples will be changing person to person. And that's fine. There's some variability in that. But if you look at them overall, you can start to see a pattern and a mean. And that's where we get really the more important data from. Take note, increasing the sample size does not reduce bias. Okay, increasing the sample size does not reduce bias. It'll probably say this later, but increasing the sample size can reduce variability, but it will not reduce bias. That's a good point, right? Yeah, I like that. All right. A safety engineer at an automobile assembly plant knows that 180 pickup trucks will be assembled tomorrow. To meet federal regulations, the engineer must select 5 of those vehicles for safety testing. Describe how to select a simple random sample of 5 trucks using slips of paper. All right, yeah. So maybe put all 180 truck VIN numbers on an equal size slip of paper and in a hat, and then just kind of mix them up and pick 5. Um, so let's see. That's kind of what we'll say. I'm gonna go ahead and pause it and then fill this in. You guys can always pause it later. If you want to come back and copy it, you can. All right, so I wrote down my answer. Hopefully you guys can pause the screen if you want to read it or copy down, whatever it is. I'm gonna move on to the question below this. Describe how to select a simple random sample of 5 trucks using a random number generator. Well, of course, it's very similar. Um, we will just have the same system where we put the numbers 1 to 180, but we'll use a random number generator to generate 5 random numbers, and then we'll choose those 5 trucks. So again, give me a second. I'll write this down, and you can copy it, pause it, whatever it is you got to do. All right, so here we go. There's kind of my response. Again, the same thing I just mentioned, but written out. So again, if you want to pause it and copy it, you can. Otherwise, I will just move on to the next example, sampling variability in A. So a recent Gallup poll found that 57.7% of a random sample of 1,940, oh, sorry, that's million, 1,947,144 Americans eat produce often. For the purposes of this poll, eating produce often is defined as eating the recommended daily allowance of fruits and vegetables at least 4 days in the previous week. Do you think that the percentage of all Americans who eat produce often is equal to 57.7%? Explain your reasoning. So the answer here is of course not. Um, this was a sample, right? And in that sample, 57.7% said that they eat produce often. And that's probably going to be somewhat accurate, but it won't be exact, right? Maybe the population's actual proportion is more like 58%, or maybe something a little higher, a little lower. We don't necessarily know. But we do know that when we take a sample, that there's some variability there, that there's going to be some give or take amount. It's not going to be perfect exact. It's very unlikely. So, but it should be close, right? It just won't be dead on. So this is what we're going to mention. Again, I'll pause it and write it down. You guys can do the same. All right, so here is my response. Basically very similar to what I had said just a moment ago. So again, you can pause it, copy it, or let me move on. I'm going to go on to B. If the sample size was decreased to 10,000 Americans, what effect would this have on the estimated percentage of Americans who eat produce frequently? So this will probably increase the variability. You're more likely to be a little further off from the actual value, right? Again, the big thing here is that if you increase the sample size, you will decrease your variability. So the opposite is true as well. If you decrease the sample size, then you increase your variability. You're more likely to have a little bit further off, right? So that's kind of what we're going to mention here. And so I'll copy that down, and then, you guys can pause it and write it down as well. All right, so there's my response. Put it this way. If I asked 1 million people, right, how often they eat produce, and they said 57%, and 57% of them said they did. But then I asked you 10,000 people, right? I asked them the same thing, and they told me 65% of them ate produce. Which survey are you going to trust more? The one where I asked 1 million people, or the one where I asked 10,000 people? Of course, the one with 1 million people would be trusted more, right? You have more data there, and yeah, that value will be uh, more correct than one with a smaller sample. All right, so let's move on. There's a backside of this time. So let's go to that. Inference for sampling. So the purpose, let me zoom out a little bit here. The purpose of a sample is to give us information about a larger population. The process of drawing conclusions about a population based on sample data is called inference, because we infer information about the population from what we know about the sample. So the process of drawing conclusions about a population based on data, sample data, is called inference because we infer information about the population from what we know about the sample. So again, when I discover that 57.7% of people eat produce from my sample, I can then infer that that same or similar percentage is true about all Americans, not just the sample, right? That's the whole point. Trying to figure out how many Americans eat produce regularly. And if my sample says 57.7, then I have to assume, as long as my sampling was not biased, then I have to assume that the population as a whole would be very similar, and about 57.7% of them eat produce. You know what I mean? All right. We got a lot of reading here, so let's get down to it. This problem says, do people prefer the last thing they taste? Researchers at the University of Michigan designed the study to find out. The researchers gave 22 students 5 different Hershey Kisses: milk chocolate, dark chocolate, cream, caramel, and almond, in random order, and asked the students to rate each one. Participants were not told how many kisses they would taste. However, when the 5th and final kiss was presented, the highest participants were informed that it would be their last one. Of the 22 students, 14 or 64% gave the final kiss the highest rating. This is greater than 20%, the expected percentage of people, if people don't have a special preference for the last thing they taste. To determine if these data provide convincing evidence that more than 20% of students like these prefer the last kiss they taste, 100 simulated simple random samples were selected. Each dot in the graph shows the simulated number of students out of 22 who preferred the last kiss, assuming each student had a 20% chance of choosing the last kiss. All right. All right. Explain how the graph illustrates the concept of sampling variability. All right. So a lot of things to kind of take away from this. The first thing is um, they do so each dot represents that you see on the dot plot represents one sample of 22 students. Okay. And they said that they did 100 of them, so there should be about 100 dots there. Remember, each dot represents one sample of 22 students. So like if I look at this dot here, just as a note, that means in that particular trial of 22 students, 2 students preferred the last kiss as their favorite. All right. So let me prepare my response real quick and I'll get right back to you. All right. So let me try to again go off what we're trying to do here. So in these 100 trials, this is a simple random sample. So basically, these trials assume, right, that they're testing if people did not have a preference. These are the likelihoods of them preferring the last kiss as their favorite. So again, the dot that I circled shows us in one of those trials of 22 students, again, this is a made up trial, um, that 2 of the 22 students preferred the last kiss. This is by random chance. This is not a actual trial. Remember, this is a simulated trial where all you're basing it on is, hey, we're assuming that again, if they don't have a preference, then we would assume that there's a 20% chance that they would like the last kiss because there's 5 kisses, right? There's 5 different types of kisses. And if it's random chance, you're choosing one of those 5 randomly, which means you would choose the last one 20% of the time. You would choose the first one 20% of the time. You would choose the second one 20% of the time. If you didn't have a preference, right, then you each kiss would have an equal chance of being selected as the favorite. And so again, all 100 trials here are simulated on that assumption. So as you can see, a lot of those trials generally are between like 2 and 6, right? 2 out of 22 students, all the way up to maybe 6, maybe 7 out of 22 students is pretty typical if, again, there is no preference. If you were just basically choosing your favorite kiss randomly, right? And you didn't have a preference to that. But what we noticed in the actual trial that we did was 14 out of 22 students preferred the last kiss. And you're going to notice here that we have one trial where it randomly gave us 10 out of 22 students chose the last kiss. Again, that was a random um, where it's a 20% chance that it would be the last one every time, and 10 of 22 got it. But as you can see, none of the simulated trials got above 10. But our one single real life trial was 14, which tells us here that that is significant, right? That was not done by random chance because all of these ones were done by random chance, and not a single one came even close to 14. So the only explanation that's reasonable is that this 14 students out of 22 was not random, that there must have been a real preference for that last Hershey kiss, and it wasn't just randomly choosing that last Hershey kiss, that they genuinely preferred that last one. If that makes sense. So let's kind of run in through our answers here because that's kind of the big explanation, but let's talk about how we can respond to these. So A, explain how the graph illustrates the concept of sampling variability. All right. If researchers take many random samples, so I'll read this one and write this one at the same time. If researchers take many random samples, take many random samples of size 22. So again, 22 students, right? From a population of students, exactly. Oh, who show no preference. Um, for what they taste last. The number of students in a sample who prefer the last kiss varies from about 1 to 10. I'm going to say with majority between 2 and 7, right? Because we see the bulk of that data goes kind of from 2 to 7. All right. In the simulation, what percent of the samples resulted in 14 or more students preferring the last kiss? So in the sample or in the simulation, zero, none of them, 0 out of 100, right? 0 out of 100 or 0% simulated um, samples resulting in 14 or more students preferring the last kiss. In the actual study, 14 students preferred the last kiss. Based on your answer to part B, is there convincing evidence that students like these prefer the last kiss they taste? Absolutely. Um, so because it is unlikely to get 14 or more students to get 14 or more students who prefer the last kiss by chance. There is convincing evidence that students like these prefer the last thing they taste. All right, this is a huge concept in statistics and one that we're going to be running with for the remainder of the year, I think. So at least um, when you think about statistics, this is the quintessential aspect of it in terms of determining whether something is statistically significant or not. It's a big part of statistics. So yeah, so if you have any questions about this, please let me know. It's super important that you understand this. So that's gonna do it for this day, though. So I'll see you in the next one. We have a quiz coming up. Make sure you're ready for that. Okay. All right. Again, if you need anything, let me know. I'll see you guys next time.